All right, so we're just going to try to scoot through this part fast because the chapter 4, the unit 4 stuff is more of a review for you. But calling these triangles right, scaling, obtuse, isosceles, equilateral, and equiangular, just kind of put that vocabulary back in our minds. The relationships between the sometimes, always, never is always fun to see about. Can it be isosceles and right? Can it be obtuse and right? Can it be right and equilateral? So making sure that we understand those. These two figures should look familiar because they were on a past quiz. So you've seen them before. These three problems here, 15, 16, and 17, are all just about the triangle sum theorem. Add them up, set them equal to 180. And down here, the solving for x and y is all about isosceles relationships, about what you can and cannot set equal to each other. Any questions on this first page? Go ahead.
I didn't know how to do number 1 and 2 on the solve for x and y.
Okay, so because this is an isosceles triangle, I can set these two equal to each other. So if the
3x minus 11 is equal to 2x plus 11.
Yeah, and that's how I got x is equal to 22. Yeah. Once I get 22 for x, I can plug it in and get a value of 55 for each of these angles, and that's what this part here is. And then I set that equal to 180 when it's added to 2y.
Can I just write 55 plus 55 plus 2y?
Yeah. That's
Okay,
this. That's this 110.
I was very lost when you put the
Mhm.
2.
Right, because each of these is there twice, right? So 2 times, and I plugged in the 11 for the x. But yeah, they were 55, so you could write 55 plus 55 plus 2y.
Okay.
And same thing here. This is isosceles. So when I set 3x is equal to that, this is actually a system of equations. So that's my first equation here. My second equation is 90 plus this is equal to 180. So this is my second equation. And I believe I had a Post-it note. I don't know where my Post-it note got to. But on the video, I solved it using a system of equations. So that's not on the test, but I'll be happy to go over it for you some other time if you need it. Go ahead, Maggie.
Could you also just put both of them equal to 45?
Yeah, that would be much simpler, wouldn't it? So because this is isosceles and because this is right, I know that each of these are 45. So that would be obviously much simpler. All right, same thing with isosceles, setting things equal to. Okay, on the back of this review packet, we had some more conversations. These were all on your Unit 4 review. So we're a refresher of the answers. When we talk about triangle inequalities, if the sum of the two smaller sides has to be bigger than that third side, then you have a triangle. And then these conversations about what has to be equal to what. Anybody want to go over or talk about anything? Go ahead, Ethan.
I had a question for number 7 and 8. I was confused on how to do that for the solve x and y. I just didn't know how to, like, the setting up the equation is always difficult for me.
Right, so for this equation, the first thing I'm going to do is set these two equal to each other because it's isosceles and the angles are the same measure.
Okay.
So my first equation is going to be 3x plus 10 is equal to 5x minus 10, and that's how I'm going to go ahead and get my value for x. Once I get my value for x, this is also isosceles, so this side length is also equal to 4y. So once I get my value for x, I get 10, which means that each of these side lengths are 40, which means that this 4y has to be added to the sum of the two remote interior angles. So 4y is equal to 80. And that's where I get y is equal to 20. Okay?
Okay.
But I don't want to spend too much time on this because this was Unit 4 stuff. So the practice and the isosceles and equilateral stuff, good to have in the back of your brain, but I really want to talk about triangle congruence. All right, anything else you guys want to talk about on, go ahead.
Number 4 for number 4.
Two sides of a triangle have length 6 and 11.
Yeah, I was lost because I added them together, and when you were on the review, you said that was like wrong. You did 22, 34. I was lost. I did 17 and something else.
Yeah, so if the sides of my triangle are 6 and 11, if I draw this sketch down here, I have 6, 11, and some unknown. My inequalities are 6 plus x has to be bigger than 11. 11 plus 6 has to be bigger than x. I didn't write the third inequality because x plus 11 is already bigger than 6. So when I write these two inequalities, this first one and this second one, I get these values for x. X has to be bigger than 5, which I wrote over here. X has to be smaller than 17, which is there. So this is just my values for x. These are the ranges, as long as x is bigger than 5 and smaller than 17.
That's all right.
Yeah, but it asks you the lengths of the perimeter. So you have to add 17 to each of these values to get that's where the 22 and 34 come from.
Okay.
So the perimeter is going to be anywhere from 22 to 34. Okay? All right. Are we good to go on page 2? All right, here's page 3. This is just like the one that was on your test before. If you know which angle is the largest angle, you only have one inequality to set up. The sum of the two smaller sides has to be bigger than the third. So that's why you get that value for x. My hinge theorem are real quick. Just keep in mind you have two sides of two triangles, two corresponding sides of two triangles that are equal to each other. That size of the angle and the size of the side opposite have that relationship. Larger side, larger angle, larger side. Some Pythagoras review, always good for you. And then we can talk about whether or not the sides of a triangle can represent, the numbers can represent the lengths of a triangle. I always find my larger side and I set up my Pythagorean converse. If the sum of my two smaller sides here, 17 and 15 is 34, so that one wasn't even a triangle. But I set it up with my converse, 37 squared, find the relationship between that and 12 squared plus 35 squared. If it's the same, it's a right triangle. If C is bigger, it's obtuse. If C is smaller, it's acute.
When we're solving for the Pythagorean theorem, do we have to put it in like the square root like this, like the what's it called?
Yeah, it depends on how you're asked. You can estimate the answer,
But if I put it
simplify the radical.
if I just put it as a decimal and not as like the simplest square root.
It depends on how it's asked. If it's asked for the exact value, you have to simplify the radical.
Okay.
All right, this is what I want to get to. So we use the distance formula here to determine if the triangle with the vertices is acute, right, or obtuse. So I went ahead and had those distances. Not a problem. Here's what we care about for today. And this is what's on your warm-up. All of those corresponding values. Making sure that you include degrees, angle signs, and segment notation along with the triangle. So geometry is all about details. So if you're talking about an angle, tell me. If you're talking about degree measure, tell me. If you're talking about a segment, tell me. If you're talking about a distance, tell me. If you're talking about a triangle, tell me. 8, 9, and 10, identify any figures that can be proved congruent. So they gave us a lot of information here on 8, and we have so much information, all of our congruence postulates work. Number 9 is one of the most missed because all of those angles match up. But notice the side lengths, there's not one corresponding side. In fact, it could be this little itty bitty one. Down here, use the given information, matching up corresponding sides, and then doing equation solving and algebra. Any questions on any of those? Go ahead, Maggie.
This is one of the four. Can you go to 12?
This one?
The 12 on the other page.
12.
One where you're.
This one up here?
Yeah.
Okay. Because L is my largest angle, I know that J, the measure of angle J, plus the measure of angle K added together have to be, no, because L is my largest angle, that means that JK is my longest side. So that means that the measure of this side plus the measure of this side has to be bigger than that one.
And then you just have to.
Yeah, and then I just solved for X. And I did it a bunch of times because it felt weird to get a fraction, so I thought I messed up. But I don't. Because that is my largest angle, that's my longest side. Nazifa?
On the bottom of the page, like number 3 goes B. Is it obtuse or acute?
I have this as bigger, so if C is bigger, that makes it obtuse.
Oh.
Right? So think about if it's like this, it's right. If it's like this, it's acute. So think about it in terms of the measure of the side C. If that side is bigger, then that means the angle is open real wide to accommodate it. So it's going to be an obtuse angle because the hypotenuse squared is bigger than a squared plus b squared. So think about it in terms of C. We good? Okay. Let's talk about triangle congruence. Is there enough information to prove that they are congruent? Good?
So if it's given that the hypotenuses are congruent, we can say it's hypotenuse led?
Yes.
Okay.
But only if you have a right angle.
Okay, but if it's not given that the hypotenuse is equal, we can't use hypotenuse led? Okay.
Anybody want to talk about any of these? 4, 5, 6, 7, 8, 9? Go ahead. Okay, so was this the one you wanted to talk to me about for? Okay, ready? This one is congruent because I have this side here. I don't know anything about parallel, so I cannot make any conversations about, I have this side, vertical angles, and this angle. So that's why it's angle, angle, side. So you marked these sides on your paper, but those sides weren't given to you, right? So see these sides here? Oh, these ones. Nobody said they were congruent. So until somebody says, hey, these distances are the same, or these are congruent, or that's given information, you can't use it. But now that we've proven it through CPCTC, you can have it, but you gotta prove it first. Go ahead.
Would you still not be able to prove it if NT and HU were parallel?
So if NT and HU were parallel, and actually they are parallel because I have these alternate interior angles, without a side, I can't get congruence. So I get these two angles are congruent anyway through the third angle theorem, but without a side, I don't have congruence. Lots of kids are messing up on the notation between the thing that says that those lines are parallel versus congruent. The little arrows, parallel. The hash marks, congruent.
Sorry, if
go
you
ahead.
have two separate lines that are also two sets of parallel
They will be, yeah. So if you have more than one set of parallel lines, they increase the number with each, like same what we do with hashes and angle bands. All right, here's, now Olivia was asking that she gets spun around with her triangles. And my advice to you is always, if you need to, redraw the triangles in the same orientation. So if I have triangle DAK, and I can call this TSK, if I have them in the same orientation, it makes it easier for me to match up corresponding parts. Same with this one. If I spin this one around, I can have JMK, and I can compare that to NKL, and then that makes it easier for me to see what is congruent. Does that make sense?
Yes.
So that's my little hint. If I want to be super, super careful that I'm not messing up any of their orientations, then I'm going to sketch this to make sure that I know that D and T correspond, A and S correspond, and for this one, K and K correspond. All right, proofs, ready? So for 5, 6, and 7, I went ahead and said, hey, these are congruent by this justification. Side angle side for 5, angle side angle for 6, angle angle side for 7. But all of that information that's not given to me, I totally now get because of CPCTC. So I get angle D and B. I didn't have it before, but now once I prove the triangle is congruent, now I have it. It's like those congruent triangles are the key to get into the snack cabinet. Now you've got all the snacks. Now you can have all the goodies of what you want. For this triangle pair, Olivia, you can see that I did sketch them out separately because I can go ahead. If I'm given that angle S and angle W are congruent, no, that's what I'm proving. I'm given the diagram. And these marks were tricky because I had 2 marks here, 1 mark here, 2 marks here, 1 mark here. So I needed this whole side to be congruent, which is why I had to go ahead and convert from congruent pieces to equal distances. And then I had to add the distances together. And then I used lots of substitution transit property of equality to get those 2 lengths equal to each other. And once I had those 2 big sides, I already had my angle R through reflexive property, and I already had this one given side here, this short side of the triangle that's here. I already had those. And my goal was S and W, so I got that through CPCTC of the congruent triangles. Go ahead.
So I did the segment addition, and then I went straight to reflexive property, then like SAS, then CPT something. But did I have to do like all the stuff in the middle?
So technically, yes. Technically, you can't add segments together. You can only add their distances.
Oh.
So we have to transfer them into mathematical values.
Oh.
So that's what the definition of congruence is. Here is where I show that RS is these 2 pieces added together. Here's where I show that RW is these 2 pieces added together. And then because everything is congruent, I start substituting in. And RS and RW I put in terms of these 2, which is why I can set them equal to each other. So all this work in 2 and 3 is to give me this pink side.
Okay.
Down here, I needed to prove those little triangles were equal to each other. And I gotta be honest with you, I missed this sentence first go around. I'm staring at the picture like, what the heck? And then I had to go back and like, oh, I almost missed this sentence. So because I had ACB, this triangle, and I have DBC, this triangle, through CPCTC, that gave me lots of good stuff. I get those two sides are equal to each other. I get those two angles are equal to each other. I get my third angle or my second angle through vertical angles. And then that's how I prove. So that was an interesting proof because CPCTC, instead of being at the bottom of your proof, gave me one of my things I needed to prove the triangles were congruent. Sound okay? All right. If you need my key, you can keep it. If you're done with it, you can put it back in the basket. Would you please clear your desks? Make sure you have a calculator. I don't want the review packets today.